In this class, we are trying to get the eigenvalues of the raising and lowering operators j plus j minus within the Jm basis. And we have seen the way we defined these operators in the previous class. And we have also seen in the previous class that this Jm basis, it's not an eigenstate of j plus or j minus. So from the previous class, from equation 15, we have seen an expression like this one: j plus or minus acting on alpha beta is equal to c alpha beta plus or minus alpha beta plus or minus 1. So this one, actually we have seen that when this raising or lowering operator, when it adds on the alpha beta states, it affects only the second quantum number beta. So there was no effect on the alpha. So from that we have generalized this expression, and we have seen that this c alpha beta is a constant which can be determined easily. So within the Jm basis, we have seen that we converted this alpha beta into j and m. Alpha beta basis we converted into this basis with the quantum numbers j and m. So we can write this expression as, in the Jm basis, as j plus or minus jm is equal to c. Now we put jm plus or minus j, then it affects the second quantum number m plus or minus 1. Now we use the normalization condition of the Jm basis to get the value for this normalization constant Cjm. So let's consider only now. So actually we have two expressions here for j plus and j minus. So for simplicity, let's consider only one expression for the raising operator, and then we normalize it. Okay, so to normalize it, what we do, we have to take the inner product of these things with itself. So takes the adjoint of this part and multiply with itself. So we will get instead of jm catch jm, what we get is, we get the bra jm when you take the inner product. Now if you are considering j plus, then its adjoint will give you j minus. Then we have this expression itself, so this is j plus jm. Now on right hand side, what we have is, we will get the modulus square of cjm plus square. Then the inner product of this thing will give us jm plus 1 jm plus 1. Now we have seen that Jm is an orthonormal set of bases, so it's a normalized set of bases. So this, if Jm is normalized, this one is also a normalized, so this will be 1. So on right hand side, what you have is Cjm plus square. Okay, so what we get is, we got an expression for Cjm plus square, and that is given by all these quantity on the left hand side. Now in the previous class we have seen an expression for the product of j minus and j plus. So it was j minus j plus was j square minus jz square minus h cross jz. So if we substitute for this in place of this j minus j plus, then you can write the expression for Cjm plus, so this will be the square root of this quantity, right? So this is jm. Now in place of j minus j plus, I write it as j square jz square minus h cross jz. Then again we have jm on right hand side. So this can be written as square root of, now you know that when j square acting on the jm basis, we will get h cross square j into j plus 1 as the eigenstate. Then we have this jm, and the second one will give us minus of h cross square m square jm, and the third one will give us h cross m. One h cross is already there, so this will give us h cross square m jm, square root of all these quantity. This is equal to square root of h cross square, you can take in common. Then what we have is j into j plus 1. Then we have m square minus m, right? Because all these kind of terms are 1. Those are normalized states. Okay, so this can be written as square root of h cross, you can take outside, so this will be h cross into square root of j into j plus 1 minus m square minus m can be written as m into m plus 1. This is the expression for CJM plus. Now in analogy we can write the expression for CJM minus for the lowering operator. So that will be given by h cross into square root of j into j plus 1 minus m into m minus 1. The only difference is that we have an m minus 1 term here, and here we have an m plus 1 term. So thus the eigenvalue equations for the j plus and j minus can be written as, with these values for the constants, we can write it as j plus or j minus in the jm basis is equal to h cross into square root of j into j plus 1 minus m into m plus or minus 1. If you combine these two expressions, minus 1, then what we have is, we have j m plus or minus 1, right? Or it can also be written as h cross into square root of j minus or plus m, the same statement, into j plus or minus m plus 1, j m plus or minus 1. So both these are same statement written in a different way. So with this we can write the expressions for jx as, so once we know j plus and j minus, we can write the expression for jx or the eigenvalue equation for jx in the jm basis. So this is, we have seen in the previous class that this is half of j plus plus j minus, then we have the jm basis, right? So if you substitute for this j plus and j minus from the previous expression, you can write it as h cross by 2 square root of j minus m into j plus m plus 1. So this is for the j plus, then this will give us j and m plus 1 state, plus you can write it as square root of j plus m, j minus m plus 1. So this is for j minus operator. Then what we have is j, it will give an m minus 1 state. Okay. In a similar fashion, you can write the expression for the jy in the jm basis. So this is 1 by 2i j plus minus j minus jm. Also, if we substitute for j plus and j minus, this will be h cross by 2i into square root of j minus m into j plus m plus 1. Then we have j m plus 1 state minus, instead of plus we have minus, then square root of j plus m, j minus m plus 1 into j m minus 1. So we have seen expressions for j plus and j minus in this jm basis. Expression for j plus and expression for jx and jy. So with this we can proceed to find out the expectation values of various operators. So you can see that the expectation value of jx, the expectation value of jx can be obtained from this expression jm jx jm, right? So this can be written as, if you take jx as half of j plus and j minus, you can write it as half of jm, then we have j plus jm plus half of jm, then j minus jm. So this is half of j plus eigenvalue equation we have just seen. So this will be square root of j minus m into j plus m plus 1. Then what you have is, you have jm on the left hand side, the bra jm. Then when j plus acting on jm will give us a state j m plus 1. Okay, plus what we have is, we have h cross by 2. Here also we have an h cross by 2 square root of j plus m into j minus m plus 1. Then we have jm on left side, and j minus will give us jm minus 1 state. Now you can see that this goes to 0 because those are orthonormal states. Jm and Jm plus 1 or Jm and Jm minus 1, those are 0. So what you get is the expectation value of Jx is equal to 0. In a similar fashion, you can show that the expectation value for the operator Jy is also equal to 0. So the average value of the x component or the average value of the y component of the angular momentum will be 0 when you simultaneously diagonalize the j square and jz operators. Now let's see what is the expectation value of jx square. So this is from the previous class we have seen that this can be written as 1 by 4 then j plus square plus j minus plus j minus j plus j minus square. So this expression we have seen in yesterday's class. Okay, and similarly the expectation of jy square is given by minus 1 by 4 then the expectation of j plus square minus j plus j minus minus j minus j plus j minus square. Okay, now if you consider the expressions for j plus and j minus here, uh, j plus and j minus here, you can see that if you take the expectation of j plus or j minus, we will get states like wow. So let's just consider only the states that we get. We will get states like jm then j m plus 1 or states like jm j m minus 1 if it is j minus. So since these are orthonormal set of bases, all these kinds of sets will give us 0. So you can say that the expectation values of j plus and j minus are 0. So since the expectation values of j plus and j minus are 0, you can see that these terms will not contribute anything in this expression, right? So we can write jx square expectation jx square is equal to 1 by 4th of expectation j plus j minus plus j minus j plus. So this is same for the expectation of j y square. So the expectation values of x square and y square are same. Okay, now since jx square plus jy square is same as j square minus jz square and expectation jx square is same as expectation jy square. What we can write it as, can write the expectation jx square is equal to expectation jy square is equal to half of expectation j square minus j z square, right? Now since Jm is a joint eigenstate of j square and jz, with eigenvalues j into j plus 1 h cross square and m h cross respectively. What we can write is on right hand side, this is half of, then for the expectation j square you can write jm j square jm minus, and for jz square we can write jm jz square get jm. This is same as half of, we know that j square acting on jm will give us h cross square j into j plus 1, and jz square will give us m square h cross square, right? So this is h cross square by 2, then j into j plus 1 minus m square. So with this we can write the uncertainty relation. The uncertainty in the x component of the momentum and the uncertainty in the y component of the momentum. So this is given by the square root of the expectation of jx square minus the square of the expectation of jx into, for delta jy we can write as square root of expectation of jy square minus the square of the expectation of jy. Now I told you that expectation jy equal to 0 and expectation jx equal to 0 we have seen just before. So the right hand side will be simply the square root of expectation jx square, all these are operators, then jy square. So this is from expectation jx square, you can substitute from here. So this will give us h cross square by 2 j into j plus 1 minus m square, because both these quantities are same. Expectation jx square and expectation jy square are same. So it's given by this product. Now since j is always greater than or equal to m, we can write j into j plus 1 minus m square. This will be always greater than or equal to m into m plus 1 minus m square, right? Or you can write this quantity m into m plus 1 minus m square is simply m. Okay, so what I'm saying is that these quantities in this bracket, this will be always greater than or equal to m because of this condition. So you can write the uncertainty delta jx and delta jy will be greater than or equal to h cross square by 2 into m, or you can write it as delta jx delta jy is greater than or equal to h cross by 2 the expectation jz, because jz in the jm basis will give us mh cross. So from this expression mh cross is the expectation of jz, right? So you can write it as in this fashion. So this is the uncertainty relation for the angular momentum components. Delta Jx, delta Jy should always be greater than or equal to h cross by 2 Jz.